Go. What is plant? Somebody's talking too much in the back. What is what is plant available forms of elements? Okay. The plant available forms of elements are determined by the form and chemical properties of those elements. What do I mean by that? Please explain what I just said. Ellswood, chime in here anytime, man. What did I just say? What are these two concepts I just read there, and what is this? Think about it.
It's what you put in, I think, huh? And what you're using, what kind of chemicals you're using?
No. Anybody else want to chime in? Okay, let's think about plant available elements. These are the elements that plants take up to create and do its metabolic activities. Okay, and it's all its life functions. Remember on the first day that we talked about this the other day. Nitrate, nitrite, ammonia. What are those things?
Gas, nitrogen, no?
They are nitrogen. Some of them are a gas. Different forms of nitrogen, correct. So, nitrogen, I mean, every molecule can pretty much be in different forms. Or atoms, minerals specifically, can go into different forms, all right? So carbon dioxide, right, is a different form of carbon than, say, carbon monoxide. They're both carbon and oxygen. One just has one less oxygen than the other, okay? So it's a different form of carbon. You can have sugars, which is, don't quote me on this, C6H12O6, I don't know. But that is a different form of carbon. Okay, carbon exists in that form. It's a sugar. So basically what I'm saying here is the different forms of the elements that are only available to plants, that plants can only take up and use as energy, are pretty much determined by the form and chemical properties of the elements. It's determined by what is it bonded with. Think atomically, just the minerals themselves. Okay? Don't look at the larger picture. Get your mind out of the soil. We're looking at a spinning ball of carbon and a spinning ball of nitrogen. Just picture them like that, atoms together. Okay? We're at atomic level at this point. They're determined by the form and the chemical properties of the element. So, whether or not a mineral can be taken up by a plant is dependent on what is bonded with that needed mineral. Okay, that's all I'm trying to say. Could be, well, we'll get there. Do you understand what I just kind of said there? Okay. I will show you different forms of these molecules and all that stuff in a second. All right, this is where it gets super complicated. Ionic charge. What is ionic charge? This is true. This was all in the homework that you guys were supposed to read. You guys should be like, oh, I know this because I read it. It's all in there. Nobody read any of it. Okay. Okay, so ionic charge means that each mineral, let's turn that camera over here. Ionic charge means that every mineral has a property about it. It is either, every one of them, positive, negative, or neutral. It could be positive, negative, positive, negative, positive or negative, positive or negative. This is dependent on what is it bonded with. If nitrogen bonds with hydrogen, I'm not not going to get too technical yet. It comes out to be positive. If phosphorus bonds with oxygen, it comes out to be negative. I'm just trying to show you that if nitrogen bonds with oxygen, it comes out negative. So it's dependent, the charge, the way it behaves is dependent on what bonds with it. And depending on what bonds with it, dictates its charge. I'll get into that in a second. But just know that something that has nitrogen in it doesn't necessarily mean it's negative or positive. You have to find out what it's bonded with. Okay? And I'll tell you how that's important in a sec. No, it can't. And I'll explain that in a sec. But all I wanted to do is indicate that these plant available nutrients like ammonia has a specific charge. Depending on, this is a different one than this, right? Depending on what it's bonded with, each one has a different charge. Charge is super important. We'll get into that in a sec. Okay? That's just the concept I'm trying to get across. Does everybody understand that concept? Got it? All right. NO3 would be nitrite. Nitrite, I think. Nitrite. Yeah, it'd be nitrate if it was 2, if it was NO2. Okay. So we covered what ionic charge is. It's basically the charge of a molecule. Every single molecule has a charge. Okay? And we're also going to talk about cation exchange capacity. Did that blink? It's going, right? That's what you were talking about. Okay. We're going to talk about cation exchange capacity. Okay. Going back to ionic charge, back up here. There's two kinds of compounds. Remember I said you could either be positive or negative or neutral? Well, the positive ones are called, it looks like cations, but it's cations. Cations, meaning positive ions. So all the ones that have a plus next to it are cations. The opposite, anion. Some compounds, I guess those are molecules as well, are negatively charged. Those are called anions. Why is this important? Well, that's because most fertilizers that you add to the soil as a farmer are this. Most of them are cations. So when I put in nitrogen fertilizer that's water soluble, it's a nitrate form, put it out, it has a positive charge to it. Some fertilizers are anions, but most are going to be cations. Okay? So, when I'm talking about cation exchange capacity, back over here, this is the capacity What is a colloid? It was in the reading. It had its own section. Okay. I'm going to talk about this in a second, but a colloid is essentially a ball of soil, microscopic ball of soil. In layman's terms. We'll get to it in a more detailed look. But essentially, let's look at this. This is maybe 1 nanometer across. Super tiny. Need a microscope, right? So we're at a microscopic level. We're looking at a colloid. CEC, cation exchange capacity. All this is the capacity for this tiny ball of soil to grab onto positively charged ions. It's its ability to hold positively charged ions. That's what CEC means, cation exchange capacity. How many cations? It's a capacity of cations that this ball of soil has. Everybody understands what cation exchange capacity is. It's a great way to measure to see if your soil is healthy or not. If you have a great exchange capacity, that means fertilizers that you put in can easily get bonded to these soil balls, and when the plant needs it, it can release them and give it to the plant. Nice, easy flow of holding on and letting go. Exchange. Can it let go of one positively charged ion and then another positive one comes in and takes its place? Does it have that ability to go back and forth? Release, let go, release, let go. Okay? Cation exchange capacity. Got it? We'll get a little more detailed in a sec. I'm just introducing the ideas here. Hey, look at this thing. Remember this thing? There's probably 20 more than when you went to high school. They're all man-made. I think only 1 or 2 of them are natural, and they're from meteors. So when you went to high school or went to school, it looks almost exactly the same. Not too much has changed as far as you're concerned. Most of the stuff that we've discovered is man-made radioactive materials, which are all down here. But for the most part, this all looks the same as it did when you went to school. I'm going to introduce you to a couple sections of the periodic table. Most important section when I'm talking about ions is all the way over here on the edge. Anybody know what these are called? It's a good try. Noble gases. Noble gases, meaning elite, meaning I'm better than you, right? Actually, meaning more comfortable. It means that these gases, all these gases and all these elements exist in space. They're out there in the universe. They're all over the place. They're on all different planets. They're not just here, right? But specifically, in the conditions in which Earth provides, the temperature, the moisture content, all that stuff, at those conditions, these specific gases, they're all gases, are comfortable. They feel nice. They feel real at home on Earth. Really at home on Earth, all right? Therefore, they are neutral. They don't react with other charges. They are called noble gases for a reason. They are comfy. They are good. They don't need anything else. They are fine. Everybody got that concept? Okay. Now, as I steer away from this line, say I take one step over and I go this way. I go here. And I find chlorine, one of the micronutrients, right? Well, since I moved one step to the left of the noble gases, remember, this is not just This is all organized, right? This isn't just thrown up to there for visual sake. There's a reason why these are put in this column and these are put in this column, right? Noble gases, I move one over. Chlorine is a 1 minus charge because it's one step away from the noble gases. Everybody understand that? Am I doing that right? Negative. Am I going the wrong way? Oh, that's right. Okay. Negative charge. It's 1 negative. So say I go over to this line. Hey, look at this one. Sulfur. We already talked about that. It's one of the macronutrients, right? If I was to ask you what would the charge be of this one, what would you say? 2 plus. Or 2 minus. Sorry. 2 minus. If I move over, hey, look at this one. There's phosphorus. What is that one? 3 minus. Okay. As we move away, we start increasing until we get to 4, which is here. We'll get to that in a second. Okay? I need you to understand right here we got 3 minuses and neutral. What does that mean? See camera. My glasses on. Chlorine, sulfur. I can't see even past 30 feet. Is it P's next? Oh, sulfur's next. P. 1 minus, 2 minus, 3 minus. Right? We've established that P is a 3 minus, sulfur is a 2 minus, and chlorine is a 1 minus. Everybody's on page there, right? Okay. What does that mean? Let's talk about the pluses. We'll get back to this.
That will determine when the bonding occurs, whether it's going to be positive or negative.
Yes. When the bonding occurs, there is going to be something left over. We'll talk about it in a sec. Okay? Let's talk about the positives before we get to that. Noble gases, right? Do me a favor when you're picturing this periodic table, all right? Think of it as a map and a globe, all right? A map is flat, right? But it represents a circular surface. It's the same thing here, okay? A periodic table isn't flat like a map. It's actually like a circle, all right? So this side over here actually connects with this side over here. So imagine folding it like a piece of paper. That's actually what it looks like. All chemists know this, that it's actually a continuous circle. All right? So if I was to say, move from my noble gases over to here, I find things like hydrogen and potassium. What would this be? Plus. 1 plus, because I'm moving 1 over from here, because it's a circle, right? What's this? What's this? What's this? What's all this stuff? Oh, that's confusing, isn't it? Yeah, we'll get into that. Forget the blue sections even there. Bring these two sections together. This is 3. This is 3. Okay? We just went from 1, 2, to 3. Forget the blue sections even there. What do we do? 1, 2, 3, and then...
The first one, the green is 1.
Right, no?
1, 2, 3.
Right, that's right. 3 and 4. Okay, here's where it gets tricky. 1, 2, 3. See what I'm pointing at? This little Tetris piece here? That's 3, and then 4. Okay?
But I thought the 4 was part of the negative.
Yeah, yes. So it can actually go either way.
Yeah.
It can go either way. It can be a 4 plus or a 4 negative. Okay? When we're talking about plants, what's coming into play here? This one and this one, right? This is one of the gas, non-mineral. And then the silicon, small kind, right? Whole bunch, small little bit. So when we're talking about silicon, usually, like I said, found in the soil, not that big of a deal as far as understanding its charge, unless you're getting really specific in the scientific side, which most farmers aren't. So for the most part, we're talking about a 4 being carbon. Carbon can be a 4 plus or a 4 negative. It's tricky. Good thing you don't have to add it, right? So, got the positive ones. Mg, right? What's in the third one? You got zinc. Three minus, 3 plus, 2 minus, 2 plus, 1 minus, 1 plus. What does this mean? I just asked you that question. It means that these molecules have 1 extra. That's actually, let me phrase that right. Missing 1 electron. Two electrons. 3 electrons. Extra electron. Electron. And so on and so on. You have an atom, right? Protons, electrons, neutrons, right? Remember that? 3 parts of an atom. All I'm saying here is, during its bonding, and while it's bonding with something else, there might be an extra proton or an extra, it's not extra, I keep forgetting, it's missing electron or 1 extra, right? Almost, remember I said every single one of these has a charge, right? Why does it have a charge? Because the atoms would not be able to interact with anything in the environment if it didn't have a charge. If they all have charges, then they can mix and match and behave funny with each other and create stars and create human flesh and all these fantastic things that it does. If they just float around in space, kind of neutral, all day long, they just bump into each other and there's no reaction and there's nothing amazing happening. They're just bumping into each other, okay? So this is how the universe works, okay? This is how wood is created. This is how the air we breathe is created. It's how every single thing is created, all right? We were all created this way. We are all made of stars. Every cell in your body is made from a star, believe it or not. It was created out in space, and somehow, some way, an environment made it possible for these atoms to react with each other and create ourselves. Okay? So, that's what I'm talking about. Missing an electron or having an extra electron. It's ionic exchange. How do they behave with each other? How do they react? Some of them are out there being negative, some are positive. What happens when a positive and a negative get together? Match made in heaven, right? Okay. These are ions. Every single element has a charge. Every single element has an ion charge. Did I lose anybody? Please tell me if you don't understand any of what I just said. I'm happy. Okay. We're made out of stars. We're all made of the same stuff. That's why I love racism. Because racists, you laugh at them. You're like, we're all made of the same thing. I'm not even indiscriminate as far as between the table and me. We're all made of the same stuff. I'm a universal, appreciative of everything around me. All right, let's talk about ionic charge specifically like I just did. I didn't want to show you this map until you understood it first, because if I showed you this first, you'd understand it right away. I tried to avoid that. I wanted to make it hard. No, I didn't want to make it hard. I wanted you to actually understand it. Okay, so let's look at this one, right? Noble gases, right? As we take stair steps up, the reason why these stair steps are up here is mainly because most of the elements that have to do with plants are up here. Okay? Plus, these down here have different... The transition metals, when it comes to plants, I wouldn't even get into that. They behave... each one behaves on its own agenda. Okay? So you have to be a chemist to really understand that. But as we move away, we have the halogens, and then we have the nonmetals. So we're going -1, -2, -3. This one says +3, but this is actually can be a 4. We won't talk about that too much. I don't want to confuse anybody. And then as we go this way, +1, 2, 3, and then here's the 4, right? Right in the middle. Does that make sense? Remember I said each one has its own characteristics? Zinc is super important as far as plants goes. It's always going to exist in the environment like nitrogen. It can't just sit there by itself. It has to bond with itself. Or it has to bond with something else to exist in the environment. Most times it's able to find itself. So it's always going to be a 2+ charge. Okay? Here's another one explaining what I just went through. Do I need to clarify this anymore? Okay. We're going to talk about colloids and the colloid complex. See if I can do this without drawing. Okay. We all know what a colloid is, right? Or at least have some kind of basic understanding.